Hope everybody's doing well. It's nice to see you all virtually and looking forward to getting some hands-on stuff that we're going to be doing as a more of a focus thing for Thursdays. And so let me go in and open this up in prayer, and then I'll get into it. So, dear Heavenly Father, Lord, thank you for the wonderful opportunity to work with each of these students. Lord, I pray that you would help them. Some of them are getting close to finishing up at APU, that you would help them as they're preparing for a bright future. Also, I'm thankful for the time that they can be drinking deeply from getting to know Scripture, the theological concepts in which we want to be guiding our lives by. And so we just offer this time to you. In Jesus' name we pray. Amen. So it's really good to see you all. And it's always kind of a hectic time getting into a new semester, but I'm very thankful that I could be sharing this time with you. And so what I wanted to do for our time together on Thursdays, as I tried to express on Tuesdays, is to be focusing a little bit more on some hands-on type of work. And so one of the things that I will do is show you the first tool that we're going to be using on the first of three. And so the first one that we're going to be using is this Digital Logic Simulator. And so just by a show of hands, did people find that? I put in the information in Canvas. And so let me just point you to the direction where that is, just to be helping out. And so I put in this page here. So if you click on this page, it's called Project Resource Information. And so there's a couple of different things. It gives you the location where you can get the information. And also there is some short videos that I put in this as well to help you get it installed. And so the first one is called a Digital Logic Design Simulator. And it's something you can get off of GitHub. And it's actually a .jar file. It's a Java file that you will be using as we start to go through this. And so I think am I sharing my screen? Are you seeing this? Let's get a positive feedback. You guys are seeing it. Usually I get a green outline and I'm not getting it right now. So I just want to make sure that you're seeing it.
Yeah, we're seeing it.
Okay, good. So as a result, you're going to need to make sure that you have Java installed. And I think you can have multiple versions of Java. I think it's Java 8 that you need to be using for this. So I'm just going to go to where I have it. So you can do this. I've done it on both a Mac and a PC once you make the connection. So for a Mac, which I'm on, you just click on the Java link. And actually, it's set to automatically do that. And so if I just click on it, it's going to open up, and let me move this over to this monitor so you can get a chance to see that. So let me just get a I don't want this to just be theoretical. So how many, either if you want to put it in the chat, if you want to raise your hand, how many people have got this installed and have it working? Or do I need to back up and go through those steps with you? Okay, good. We have several people that are downloading it. And so you could argue like those Thursdays are, quote, a little bit more of a lab kind of feel. So let's get you guys up to speed. And so David, Isabel, and Avery, if you want to let me know how it's working for you, please let me know. So while you're doing that, there are a couple of videos. This is more of how to get things installed. I also have some additional videos, and there might be a little bit of overlap, so I apologize. Yeah, these are the same ones for installing it. But then I have some demonstration videos, mostly for the third project. Okay, it was nice to get a chance to chat with you folks in class on Tuesday, and then after class, several people were asking some questions and trying to think of how that they could start to be working on their project proposal. And so getting into this might be a little bit getting the cart before the horse, but let's see if we can try it and have you see this. So what I'm showing here is something that I ginned up yesterday. And so typically when you have these logic gates, and so does anybody remember what are the three major logic gates? And if you haven't, because you haven't covered it yet, I just want to have you think about it. Anybody have an idea? I know we have some folks on the engineering side. What type of logic gate is this? Does anybody remember?
AND gate.
Yeah, it's an AND gate. And so this is one of the three basic type of logic gates. And so what that means is you have to have two inputs to be true for the output to be true. And so let me just I'll just show this in action, and then I'll back up and I'll start to make this for you to see what it is like. And so we have these AND gates. We have these wires that connect. These are basically a push button, if you will. You push it in, it's positive. You deselect it, and it's a zero. So like if I do that, that's pushed in. It illuminates the wire, so you can see that it's on. I also put in a virtual view of what an LED looks like. When we get into the third project, when we're working on the Arduino, you're going to get a chance to have real LEDs. And so in some ways, this could be something that is a precursor for what we're going to be looking at as we move towards some of the latter projects. So what happens if I push this one? Anybody have an idea what will happen to this? Since this is an AND gate, this is true, this is not true, so it's not illuminating the output. What will happen if I push B? Anybody have an idea?
Will it give an error?
What was that?
Will it give an error?
I don't know what you mean by an error, but it will change the condition. And so let's just show you what happens when, so I did that. So now both of these inputs are true. And so therefore for an AND gate, that means that the output is going to be true. So now it's passing that information to that next gate. And just as a way of giving a little bit of positive reinforcement, this is an LED that's giving you, let's pretend like we had this in digital electronics. You're not going to be able to see the result of that. And so that's one of the reasons why having things like this is a helpful way of having a diagnostic. So what would you think would happen if I push this one? Anybody have an idea?
The AND gate on the right will also read true.
Right, yeah. So basically, the most simplest kind of logic scenario would be something like this. And remember I talked about for the digital logic, having as a minimum of 3 inputs that you want to be looking at of how you could aggregate navigate those two together. And so this is how I'm actually programmed a way of when three inputs are true, the output is true. So most folks are familiar with programming in software, but in a sense, I'm programming a scenario here the way that I would like. I was talking to one or more of you who were interested in cybersecurity. And so one of the ways that you can be thinking in terms of an abstraction, let's say that they're needed to have three type of things that you're going to validate someone's identity. And so let's say that they have a password, say that you have a second authentication source, that they get a text to their phone, and say something else. Another common thing is that you have a prompt question, what's your mother's maiden name, or something like that. So this would be a way of how you're having a guard before somebody gets access to all the resources that are available. So this could be like the first of three digital logic circuits that you could be developing. And so that would give you an idea. So David, Isabel, and Avery, since you were just downloading it, why don't you give me some responses? Did you get it working, or do you need me to help you through some of that?
I have it up and running. I just need to drag the file into the little box that it's asking in the let's get started page of it.
Okay.
Can you actually walk us through installation? Because I don't know how to install it. I just tried to open it to run it in Visual Studio, and I'm getting an error. So maybe I'm doing something wrong.
Okay, so Wasim, do you have a Mac or a PC? Just give me that information so I
PC.
PC. Okay, so do you have Java installed?
I do.
Okay, what version of Java?
I'm not sure. How do I check?
Okay, well, let me just put that aside for a moment. I'm not quite prepared because I don't have Java involved in a virtual machine. Otherwise, I'd pull that up. So I may have to flex a little bit here, but let me try and see what I can do. So you have it in a folder. And so if you right click on that file, there should be a way that you can help Windows be aware that you want to open it up with Java. And so there should be like an open with. Do you see that, Wasim?
The file is digital. It's called digital, or
Right, digital.zip, and then you need to extract it. You want to get to a digital.jar file. That's the one that you're going to open.
I'm getting open with Visual Studio, but Java is not listed as an option. Maybe I don't have Java installed anymore.
Yeah, you might want to double check that.
Okay.
Anyone else having problems? How many people successfully got it to open? Let's just go with that. Show of hands or in the chat.
Mine's working.
Okay, good. So we got several people that are working on it. Okay, good thumbs up. And Oates, is that a question, or are you just saying that it's working for you?
It's just working.
Okay.
Can you hear me?
Maybe got it to open. Okay. Kyle, it sounds like you're still working on it. I got it. Okay, Riley, great job. So let me go ahead and try and build a circuit. And so some of you who are already there, you can follow this through with me. And so I'm doing this a long way. This should be similar to what you would do for Windows. Eventually, you can get this so with an auto identify. And so you'll get a I got multiple screens, so I have to drag this back over to the one that I'm sharing. So I was showing you this already. It's a little bit quirky in some ways until you start to get into the rhythm of how it works. Oates, I can't hear you. You got it working? Good. Riley, thank you for sharing the link in case someone didn't get that. I put the link in Canvas, but hopefully I did make it too cryptic that you weren't able to find it. So here you got this blank canvas, and what you want to do now is to be putting in a component. And so what we're going to do is we're going to make an AND gate. So you just click on that, and you can actually put it wherever you want. Okay, so for a typical AND gate, you only have 2 inputs, but we're talking about 3. So we're going to have another component. So we want to put another AND gate. And so I'll just put it over like this. You can actually make this as big or small as you would like. And get it going the right direction here. So next, we want to do some connections. I'll do it for this one. So you see how when I put my mouse on it, it's red. If I click on it, it turns, I'll just call that green. I know that's not exactly, but, and then after, when you do that, you'll get this little wire coming out, and voila, you just drag it to where you want, and it'll get there. It's a little bit quirky, but I think when you start to get an idea, you'll get a feel for it. Next, we need to have inputs and outputs. So this is this input. It looks like a push button. And so when we're working on the Arduino unit, that's something that will be familiar to you. And so I'm going to get 3 of those. Line them up over here. And the same thing, you click on it, you get the changes color. And so this one's a little bit more tricky because I need to have it go up 1. So what I did is I went over like this, clicked on it, it went up there, clicked on it, it went over there. And so I got those 3 connected. And then I want to have an output. So the double circle line, have that. And I'm going to hook it up like that. And so that's the circuit that I had before. And let me show you another thing that I just found out, or actually refresh my recollection. If you right click on the component, you can actually put a label. Right click on this one, I'll put a label there. Right click on the third one. And then we got a label for that. And then put a label for the output. Okay, anybody get something like that on their desktop? Okay, good job, Riley. Once you get the feel for it, it's not too complicated, and it actually can start to be fun. And I hope they'll get to that point where you'll experience that. So let me click on this analysis. So one of the things we're not going to get into too much, but this is one of 3 ways that you can be giving a summary of what you're trying to express with this program. It's with the digital gates. Another thing that you can have is the expression. And so for those that have taken discrete mathematics, this might be familiar to you. It's basically Boolean algebra. This may not be the simplest way of looking at the expression. And so this little caret sign, upside down caret, is and, so B and C. Well, actually, I have to think about it. That's not very simple. It's, you know, I would do it a lot simpler than that in terms of expression. But another thing that you can be having is, trying to remember which one is it. This one, yeah. So this is a truth table. So I'm not sure, it should be giving us a 1 at the output. So let me see what happens. This may be from, let me see what when I start to run this, what happens. So this is what I had before. This situation here, this should be showing a 1. So I'm not doing something right, and I'm not quite sure why. Let me go to that other file that I had open. So did everybody get something like this? I got a couple folks, had a few more minutes. Basically, for your first digital logic, the first of 3 digital logics, I'm perfectly fine if you do this, but remember, what you want to be doing is not just having a circuit. You want to, what is the purpose of that circuit? And so whatever that is that you're trying to think in terms of your overall plan, that's what you're going to be capturing. And we can talk more about that if some of you are still trying to think that through, but I'll just put that out there. So I'm going to just open a recent one. This should be the one I had. I'm just going to discard it. So let's see, I'm going to check something here, see if I get the. Yeah, so I'm not quite sure why the other one didn't have it. Maybe because I hadn't saved it. But this shows you the situation where it gave the 1 at the output when all 3 are true. And so that's what you want. And then for an expression, let's see, this still gives a quirky type of expression. I'd have to do the algebraic manipulation, but I'd be willing to bet that this would be the same as just having A plus B quantity, that quantity, then you would have C. And so I could convert it into this kind of a notation. So I'm just going to put that aside. But anyway, this is another way that you can be figuring it out. It's like, what if I wanted to have a slight change to this? And so let's start to be talking about, say, like a second circuit. And so I'm just going to do a new one again. And I'm just going to replicate real quick what I had before. Do a couple inputs. An output. So that's what I had. But now let's modify this a little bit and say, instead of having this one to be this way, we want to have this to be inverted. So the way you delete things, you have to left click, and then you can highlight it and then delete it. So if I wanted to have this to be inverted, what do you think I'd have to put in there for that digital logic? Anybody have an idea?
Not gate.
Yeah. So let's go ahead and just pull out one of those. And here we can see the logic. And see, this is the not right there. Let's put that in there. So now if I run this, you can see how this automatically, whatever is the input is going to be the opposite. So if I click on this, then the output goes negative, or false. So you can see how that is operating. So if I click those other two, this one, that's going to be true. And the situation that you're going to have there, this is the only one of those scenarios that you'll get the overall result comes out that way. So yeah, I get the same thing. I think I have to save this to get it to work. So maybe I'll go ahead and do that. I'll put on some labels here. Okay, so curious if that makes any difference. Okay, well, I'm gonna have to figure out that offline. I'm not gonna waste too much time for this right now. So this would be how you would start to be getting into more complicated scenario of logic. So let me just show you some other examples. I won't go through them as quickly. I won't go through them now, but just to give you an idea. So this is an illustration that has an and an OR gate. So if I was to run that, you can see that since this is an OR gate, it doesn't, this other one doesn't actually matter what it is. It's going to put the result. And so in a sense, it's almost like the C input doesn't make any difference for this scenario when A and B are true. Let me see if the analysis works on this. So yeah, so this one works. And so there's something that I'm not quite sure why when I was just doing it. It gives more scenarios in which you're going to get a positive output. And so this is like, now we've seen a couple type of circuits that we can be using, 2 examples. Okay. So any questions on that? Okay, well, I'll move on. You can feel free to play with that, but hopefully that's taken a little bit of the mystique out of the first project and giving you a sense of what it is that we want to try and accomplish as we do things. And so you can see how this is at a fairly high abstraction. And so just like I was thinking of a cyber scenario example, we're just trying to be thinking about how the logic might work. Are we capturing it? We're not going into 3 or 4 layers down about how we're going to actually code it and what would be the prompts that we would make for a person to try and authenticate to a system, what type of language we're writing it in. So that would be in a software scenario. On a hardware side, we aren't talking about, so let's say like you had a front panel and that you had to be inputting different type of information, kind of the sky's the limit that where you could be going with that. And so you can just keep that in mind. Okay, so last time we went over fairly quickly this first chapter, and also just had a conversation to, let's try and get this to work. So we talked about the basic concepts in computer evolution. And so we got a chance to be thinking about that. I think when I do this now, I can't do anything else. So maybe I won't do that. Let's go back to my regular pointer. Okay. We highlighted a few charts that I pointed out last time. How you drill down from a high-level computer with the von Neumann architecture. Anybody remember me saying that last time? Maybe you don't remember what the components are, but anybody remember the von Neumann architecture? The von Neumann architecture is these 3 things. That's the CPU, the main memory, and the input and output. And an architecture can oftentimes go down various levels. And so the von Neumann architecture talks about aggregating things in a certain way. And the way that we have in this textbook, it looks at the integration being a 4th element, the system bus. And so that's sure definitely one way that you can be thinking about it, and that there's not a problem with that. We got a chance to look at a motherboard in various ways that they are portrayed. And then in the second chapter, we started to look at, well, how do we look at how good is a processor? How good is a computing system? Can I run it on a laptop? Do I need to run it on a supercomputer? Do I need to have a cluster? Or maybe I don't even need to run it on a laptop. Maybe I can have an embedded system using a microcontroller. And so these are some of the things that unfortunately it goes to about 2010. And so what has happened recently is Moore's law, if you've ever heard that, and I mentioned it briefly before, is that there's been a flattening out, that you can't make the electronics any smaller, get more transistors into a tiny little area. For a variety of different reasons, we're getting closer and closer to atomic scales, and to be having that much power in such a small density, it makes it pretty difficult to make things work. But one thing we have seen is an uptick is the number of cores, and this has continued to be increasing. So that's one way to be thinking about where things are going. And I think I just included one chart from chapter 2. So I'll just go back to the table of contents and have us think about that a little bit more. So what are some performance concepts? We can be thinking about the processor speed. This is typically, for a long time, was like, how fast is a processor? 1 gigahertz, 2 gigahertz, 3 gigahertz. Then it was like how many cores. That's kind of the thing that started to come together. How many GPUs do you have? And so really another thing is how many instructions are you doing per second? And that is another way where you could start to be thinking about, well, how are you going to be benchmarking the performance of the computer? And so the details of this chapter gets into the specifics, and you can be thinking about that. There's various types of benchmarks, standards like the spec benchmarks. And so that's some of the stuff that you want to be thinking about it. It's more complicated than what you would think. It's not like we're going to go into track season in the spring and everybody races, stands at the starting line and they do a 100-meter race, and whoever finishes, it's very clear because all of their quote architecture is the same. Well, what you'll find is that the type of program that you're running makes a difference. The kind of thing that you have underneath the hood. If you go like into Formula One racing, they have to have certain types of limitations of what you can and what you can't do with your car. And so these are the kind of things that start to come up when we start to be thinking about performance. And so, and then we get into the application. If you're focusing more on something like image processing, that's going to be a lot different than just having a platform when you're going to be doing sending email and doing web browsing. And so this is where that dichotomy of like, well, should we be using kind of the bread and butter processor that's been around for a long time, the x86 architecture, where recently there's been more movement of the desktop is having at least part of their processing is done with an ARM processor. So we see that a little bit in the things that we're talking about, that we'll be going back and forth between those two types of processors. Different types of input and output. Some things are quite low, but you would be dead if we didn't have them, keyboard and mouse, versus like having a Wi-Fi or Ethernet. Interesting, I just got a fiber optic in our home, and it's all of a sudden things are a lot faster. And this is the first time for a while that I've seen that Ethernet always tends to be faster. And like you can get 1 gigabyte and 10 gigabyte Ethernet. And now with the latest Wi-Fi standard that's just coming out is something called Wi-Fi 7. And so hopefully there still would be a parity that we can have things going either wirelessly or with wired coming together. So there's just a lot of stuff that are contained in terms of how we're trying to be thinking about our overall computing and how fast it is and things like that. This is the figure I showed you, and then I didn't really get into some of these other charts. So anyway, so I'm not going to get into some of the details for this benchmarking because it gets a little bit more complicated than I would like, and it's not too important for the things that we're thinking about. Here is a chart of some performance factors and system attributes. We're going to be getting a chance to be talking about instruction set. And so one of the ways where that will be coming up is, I mentioned two terms, a RISC, a reduced instruction set computing, and CISC, a complex instruction set computing. And so ARM goes in the direction of having a simple set, and so not as many instructions, while Intel and AMD, kind of following in the footsteps of Intel, has a more elaborate instruction set that they deal with to try and have things done at that level in terms of optimizing and think how that's going to impact their performance. So it's a dichotomy. If you're going to be doing a PhD thesis and you're doing a lot of modeling with scientific notation, you probably are going to want to go towards more in the direction of a complex instruction set. What about the compilers? you know, how easy is it to do a compilation of these instructions? What type of processor implementation are you going to have? I mentioned, and we'll be coming back to this, is it going, if we're going to have multiple cores, are all those cores going to be the same? That's not, doesn't have to be the case. And then we want to be thinking about if there's any cache or buffers that's going to be helping with performance. And another thing that's interesting that will be coming up as we press forward in the course is the speed of the processor is like orders of magnitude faster than memory. And so this is one of the things that has started to cause issues. If you want to continue to have performance, but you have this one part of your architecture that's lagging behind, that's going to be a huge issue. And so there's various ways of how you can be helping that out with caching and buffering. And so that's an example of something that can be thought about to try and help things overall. So these are just getting into more details about the setting things up for coming up with some benchmarking principles. So what it would be nice if you could write something in a high level language and then compare one thing to another. You could make it portable across different machines. That would be good. So you're using a language and a program that would be the same. And so you're trying to limit things and so that you can do an apples to apples type of way of comparing things. The spec stands for System Performance Evaluation Corporation. And so they've come up with a couple different ways of doing that. I'm not going to get into that, but here's an example, spec CPU 2017. And just some more details to back this up for different ways of coming up with a standard that is agreed upon in industry. And so that's going to be it. I'm not going to be focusing too much on doing lectures on Thursdays. It's more going to be doing things in terms of more of a lab format. So I'll stop sharing my screen